Hello everyone. In this lesson we are going to learn about ordinary differential equation, and we are going to solve such kind of differential equations using different techniques. So in this lesson we are going to learn about Euler's method. That is the most basic formula or method for solving an ordinary differential equation. Okay, so let's dive into the details of solving these such kind of differential equations. So what is a differential equation actually? You have seen we can easily numerically calculate or analytically calculate the differentiation of a function. Okay, whenever we have equation and in that equation we have different differential terms, then we call that equation a differential equation. Okay, so in a differential equation a lot of differential terms is a single one or two terms or three terms or many differential terms can actually appear, and that's why we call it a differential equation. Okay, so if this is the differential term, the v is the dependent variable and t is the independent variable. That means we are actually differentiating v with respect to t. Okay, that is what it means actually. So if we say we have a single independent variable, let's say here time is the independent variable, and in the whole equation, in the whole differential equation, we have only a single independent variable t. So if this is the case, that we have a single independent variable, then we call the differential equation an ordinary differential equation, or in short ODE. Okay, so in ordinary differential equation we have only a single independent variable. But if we have more than one independent variable, let's say we have 2 or 3 or 4 or more than 4, then we call that equation a partial differential equation, or a PDE. Okay, so that's the difference between ODE and PDE. And whenever we are solving the differential equations, we are just finding the value of the dependent variable. Okay, let's say this is the differential equation where we have this differential term of v, and our purpose is to solve the differential equation and find the values of v. Okay, so that means we are not in the final solution we will have no differential term, we will have the results of v. Okay, so that's the main purpose actually. So graphically, what is a differential equation means actually? In an ordinary differential equation, if we have let's say this is the differential equation. Okay, so in this differential equation we have a single differential term dv by dt, so that means, and we have a single independent variable. That means it's an ordinary differential equation. Okay, so we will see what graphically this differential term means actually. This means the slope of the dependent variable. Let's say v is a function of t, so we will have a curve, and whenever we differentiate that term, whenever we differentiate the value v with respect to t, we mean we are actually calculating the slope at a specific point. So differential with respect to a single variable means the slope of the function, so it's the slope. So we will graphically see what these actually mean more clearly. Okay, for now let's say we have this differential equation, and it is an ordinary differential equation, and it is called the first order differential equation. Why? Because we have only a first order differential term. Okay, but if we have a second order differential term, then we will call this equation a second order differential equation. Although we have a single first order differential term here, but whenever we are calculating the order of a differential equation, we consider the highest order that is available inside the equation. So in this case we have the highest order to be 2, and that's why we call it the second order differential equation. So we can easily convert a second order or higher order differential equation to a first order differential equation, because we can easily handle the first order ODE. So we can easily solve that first order differential equation. So sometimes it's very handy if we just convert a higher order differential equation to a first order differential equation. So we can easily do that by just converting the independent variable. Let's say in the second order differential equation we have the independent variable t. Okay, so we are going to introduce a new term which is y, and y is equal to dx by dt. So if we just differentiate the value y with respect to t, we will see that dy by dt means differentiating this term again, that means d square x by dt square. So if we just substitute these values dx by dt and d square x by dt inside this second order equation with these two new terms, we will get that when the new equation is actually a first order differential equation with an dependent variable to be y. So we have a new dependent variable here, but the whole equation has been converted to a first order differential equation. So that's how we can easily convert a second order, third order or higher order differential equation to a simple first order differential equation. Okay, so let's see some of the examples, some of the practical scenarios where these differential equations actually appear. So we have just covered the simple ordinary differential equations. So there are lots of engineering applications where these first order differential equations arrive. For example, the Newton's second law of motion, if you remember, the derivative with respect to velocity, that means the acceleration is equal to force divided by the mass. So that's the Newton's second law of motion where the first order differential term appear. Similarly, we have the Fourier's heat law, Fick's law of diffusion, also the Faraday's law, voltage drop across an inductor, which can be easily calculated using these first order differential equations. Okay. So some of these equations have analytical solutions, but some do not. So in those cases where the differential equations do not have analytical solutions, we are going to use the numerical solutions, and that's why we need to know some of the methods that should be used for solving a differential equations. Okay. Now let's graphically see what a differentiation with respect to a single variable, that means an ordinary differential equation, mean actually. Let's say we have this function y, which is minus 0.x5 x to the power 4 plus 4x cube, something like that. So that means it's a fourth order polynomial. So if we just plot this curve, it will look like this. So this is the plot of this function y. Okay, so if we just differentiate this curve, that means if we differentiate the values of y, we will have a new curve, that means the differential curve that looks something like this. Okay, that means this is the curve of y and this is the curve of dy by dx. That means the differentiation of y with respect to the independent variable x. Okay, so now let's see how we can actually get this curve from the original variable curve. Okay, how we can just derive this curve. So in the initially at the first data point in the original curve, we draw a tangent to the curve. Okay, that this red line denotes the tangent to the curve at the initial data point, and if we just calculate the slope of this tangent, that will mean the differentiation of the y variable with respect to x at this initial data point. Okay, similarly at the next data point, we again draw a tangent line and we calculate the slope of that line, and we will have a differential value which will look like this. Okay, similarly at the next data point, we again draw a tangent line and calculate the slope and get the differential value here. So differential value is nothing but getting the slope of the tangential line at the specific data point. Okay, so let's see at the just at this point where the function reaches a local maximum data point. So at this maximum point, the tangent becomes horizontal. So if the tangent becomes horizontal, that means the slope of the tangent line becomes 0. That means the differentiation becomes 0. So that's why at this data point the differentiation of the function is 0. Okay, beyond this point, the tangent line now turns to the negative side. That means now we will have a negative slope because the tangent has now directing downward. That means we will have a negative slope. That's why we have a negative differential value here. Okay, this is the negative value. Similarly, if we just move on, we will see that at this local minimum point, again this tangent becomes horizontal. As a result, the slope becomes 0. That means the differential terms become 0. Okay, that's how we calculated the differential curve from the original curve, by calculating the slope of the tangential lines at each of the data points. Okay, Now if you look closely at these data points, extreme data points where the function becomes maximum or minimum, at these points the differential becomes 0, okay, because the tangential line becomes horizontal. Okay, so our purpose is to calculate the original curve. That means we will be given this differential curve or the differential values, and we need to calculate the original values of the dependent variable. That means we will be given this differential curve and we need to derive this original curve. So that is the purpose of solving a differential equation. We will be given the differential curve and we will need to find out the original curve. So that's the purpose of solving a partial or ordinary differential equation. Okay, so first of all we are going to cover the Euler's method. The Euler's method is the most basic method for solving a differential equation. So if you just in Euler's method are actually applicable for simple differential equations which look like this. That means dy by dx on the left hand side, and this derivative function can be represented as a function of x and y. So if this is the case, if this is the differential equation, if the differential equation looks like this, then we can apply the Euler's method easily. How? Let's say this is the function df and this is the f function, that means the original function, and we are given the differential values at different data points. Let's say at the point xi, if we just draw a tangential line to the original function, okay, and if we can easily calculate the slope. The slope which is denoted as phi. Okay, from the slope equation, slope is denoted as the height divided by the width of the base. That means we can easily calculate this formula, yi plus 1 equal to yi plus phi times h. Okay, yi is the initial data point and i plus 1 is the next data point. H is called the slope step size, or the step size, which is the difference between the xi plus 1 and xi, and phi is called the slope. That means we can easily derive this formula, which is actually the slope of the function, from the slope of the function, and we will see that this phi term, that means the slope of the function at xi, can be easily calculated from the differential curve. Since in the question or in the differential, whenever we are going to solve a differential equation, we will be given the differential terms at each of the data points. That means we will know the value of phi at each of these data points. That means on the right hand side we will have all the terms available. Okay, we will know the xi term, we will know the yi terms, we can also know the phi term. So we can easily calculate the approximated value yi plus 1 at the next data point. Okay, so although the original value is here, but we are just approximating the result here, yi plus 1. That means we have a huge amount of error. So this error can be minimized if we just reduce the step size. That means if xi plus 1 is closer to xi, in that case the yi plus 1 will be also closer to the original value. That means by reducing the value of h, we can increase the approximation result. So once we know the term yi plus 1, we can easily use that value to calculate the next value, that means yi plus 2, and similarly using the yi plus 2 value we can calculate the next term. Okay, and so on. So that's how the Euler's method actually work. So this is the function, and we have the true value here, and we have approximated the result with the Euler's method, which is at this point. That means this term, this small segment, is the error. Okay, so this error can be minimized actually by reducing the step size, that means reducing h. So this phi term, as I have already said, this phi term can be easily calculated by the values of the differentiation of the original values at different data point. Okay, so this phi term can be easily calculated. So f of xi yi, this means actually the differential at the point xi comma yi. Okay, so now let's see how we can solve the differential equations by simply using the Euler's method. So we are given the differential equation here. Look at this. This is the original differential equation, and we are just going to rearrange the differential equation something like this. Dy by dx is on the left hand side and all the other terms is on the right hand side. So this is the first task. We need to rearrange the equation in this way. Okay, so on the right hand side we can easily calculate the differential at different points of x. Okay, so this is the differential equation, and these on the right hand side for different values of x we are going to find out the different values of the differential. That means we are just going to, using this equation, we are just going to find out the slope of the function at different data points. Okay, now we are given the data range. That means we are going to find out the value of y from x equal to 0 to x equal to 4 with a step size of 0.5. That means h is equal to 0.5, and we are given the initial conditions, which is at x equal to 0 the value of y is 1. This is the initial condition. Why this initial condition is given? Because based on this initial condition we are going to find out the next terms. That means yi plus 1, then y, using yi plus 1 we are going to calculate yi plus 2, and so on. Okay, also we are given the original solution here. We will just use it for comparison purpose. Okay, so on the first step, this is the original Euler's equation, Euler's method. So here the f of xi yi, this can be calculated from this original differential equation. Okay, so we are just going to find out the first point. That means the we are given the initial data point to be 0, and we are going to find out the value of y at data point 0.5. 0.5 is the step size. So this is the first data point. We are going to calculate the value of y using this equation. So at data point 0.5 the value of y is yi. That means the value of the function at previous data point is 0. That means at x equal to 0 we have the function to be y of 0. So how we can calculate this y of 0? We can easily get this value from this initial condition. At x equal to 0 we are given 1. Okay, then we are going to find out the function value. That means this f of xi comma yi, this is the differential value. So how we can get this value, which can be easily achieved from this original differential equation? Inside this equation we are going to substitute xi comma yi. That means the previous xi comma yi, the present xi is 0.5 and the previous xi is 0 and yi is 1. That means we are going to substitute in this equation with x equal to 0 and y equal to 1. Since there is no y term here, so this one will not be used here, but remember this differential equation can also contain the y variables as well. Okay, so then multiplied by the step size, which is 0.5. so if we just calculate this, we will get that so we will just calculate the f of 0.20 comma 1, which is 8.5, and then we get the value to be 5.25. okay, so this is the function value at x equal to 0.5. now based on this value of function at x equal to 0.5, we are going to calculate the function value at the next data point. The next data point is situated at 0.5 plus h. That means at x equal to 1. Okay, so in the first step we are just going to calculate the original solution. We can calculate the original solution from the originally given curve, since we are already given the solution here. So we are just calculate the value with x equal to 0.5, and the value turns out to be 3.21875. so if we just calculate the error is approximately minus 2.03125. so in terms of percentage, this error is approximately 63.1%. that's a huge error. Okay, so in the next step, so if we are going to find out the value of the function at x equal to 1, and we are just going to do that using the values of y of 0.5. okay, so we are just similarly going to find out the values, and for that purpose we need to find out the slope from the original differential equation, and we have already got the value of y of 0.5 from the step 1. We are going to substitute these two values here, and then we are going to get the value of y of 1 to be 5.875. and at this point x equal to 1, the true solution is 3, and we have got the result 5.875. so if we just calculate the percent relative error, which is approximately 95.8%, which is a huge error. So in this way we can easily calculate all of the approximate values. So these are the x values that we are going to use to calculate, to approximate our results, and these are the true results, and these are the approximated results from the Euler's method. So if you just look at these error terms, there is a huge errors at all of the data points. Okay, these errors can be easily reduced if we just change the step size. Okay, so this is a curve, this is the true solution, this smooth curve, this is the true solution, and we have just used Euler's method, which with a step size of 0.5, and we have got these results. So look at this, the approximated result is far away from the true result. So if we just reduce this h term, that means if we just reduce the step size, we see the approximated result gets closer to the true solution. Similarly, if we just go on to reduce the h more, then the approximated result will converge to the true solution. Okay, now let's see, there are two different kinds of errors in Euler's method actually. Whenever we are going to solve the ordinary differential equations, it's not just the Euler's method. Whenever we are going to use more complex method, there will be two different kinds of errors in solving such different ordinary differential equations. The first one is truncation error, and the second one is round of errors. But the truncation error has two different terms. The first one is local truncation error, and the second one is propagated truncation error, and summing these two terms together we will get the global truncation error. Okay, so what this local truncation and the propagated truncation error means: the local truncation error is the true truncation error that we actually mean. That means in all of these cases, at a single step, what the error that we get, that is the local truncation error. But what does the propagated truncation error means? Since this is an Euler's method, or we are just using the Euler's method as a reference, in Euler's method we have seen that based on the initial point we are just approximating the next data point. Okay, and so on. That means we are just calculating the data point at a specific point by using the help from the previous data point. Okay, so that means if we have already have some errors at the previous data point, we will have more errors at the present data point, and since we have some more errors at the present data points, in calculating the next data point we will have further more errors. That means the error is actually propagating. So we have actually the local truncation error, and side by side we will have the propagating truncation errors. That means the error is actually propagating. The more error we have on the previous step, the more error we'll have on the next step. Okay, so that's how the truncation error is actually propagating. So we will have two truncation error terms. The first one is local truncation error, and the next one is propagated truncation error. And if we just add these two terms together, we will have the global truncation error. Okay, so we have already know the significance of a round of errors, and this is actually more related to our computational facility. Okay, so in this lesson we have learned about the basics of differentiation. We have learned about the ordinary differential equation. So what graphically an simple ordinary differential equation means actually. Okay, so we have known about the orders of differential equation, and we have seen many applications of differential equation, and we have just used the Euler's method to solve a simple ordinary differential equation. Okay, so similarly we have also solved a differential equation, solve a system with Euler's method. Okay, and we have seen that the errors of the Euler's method can be easily reduced by reducing the step size. If we just increase the step size, the error will increase, but conversely, if we just reduce the step size, the error will also reduce. So I have just attached the MATLAB code for Euler's method. So if you want to see how an Euler's method can be used for practical purposes in MATLAB code, please go through that code and try to understand each of the line of the code, each of the codes. So in the next lesson we will see about some more aspects of Euler's method and some more advanced method. So till then, thank you so much.